Welcome. This video is going to be on building a 4-layer PC board. Up until now, all of my projects have been 2-layer PC boards. I've always wanted to do a 4-layer PC board, but I've never done one before. So this is going to be the first one. So what you're seeing now is the whole board already assembled. This is a Z80 single board computer that I've designed. It's mostly a combination of my other projects, of course influenced by the RC 2014, influenced by Sergei Kislev's Zeta 2. So you'll see some elements of those in here. But I've always liked the idea of a single board trainer. I remember getting the Heathkit catalogs back in the day, and they would have the Heathkit single board trainers, and they cost a fortune. I could never afford one. So I thought I'd, build my own Z80 trainer. So trainers that you interact with over a keypad and display can be kind of boring, so I wanted to do something a little bit beefier that adds some complexity. So this thing is actually powerful enough to run CP/M. It's got onboard serial port, onboard I/O, onboard flash drive, onboard RAM disk. So this kind of spans the whole continuum from a simple trainer that you could interact with through a hex keypad to something more powerful that you could connect a terminal to and actually run games and other programs on. So what does this thing have? It's got a hex keypad. It's got a total of 8 TIL311 displays. We've got a Z80 CPU, a crystal that runs the CPU. Over here we've got some single stepping stuff. We have an RC 2014 compatible expansion adapter. So over here we have the standard Z80 peripheral stack. So we've got an SIO, that's a serial I/O chip, a CTC, the counter timer, and the PIO, which is parallel I/O. Over here we have the flash ROM. This is 512K flash ROM. Includes everything necessary to boot up CP/M, plus plenty of space for a ROM disk for holding your CP/M programs and games and whatnot. ZIF socket, just flip that up, comes right out, put it back in, flip it down. And then down here's a 512K RAM. The address decoding, I did something that I've never done before. Rather than the standard address decoding using 3 to 8 decoders and such, I went with using programmable array logic. Okay, so I started out doing the usual thing that I would do for a 2-layer board. I laid everything out in Eagle with the schematic. Then I went into the board editor, put my components where I wanted. Then I told it to auto-route it. I know a lot of people aren't fans of the Eagle auto-router, but I do tend to use it a bit in my projects. And this is what we ended up with. So we ended up with about 600 vias. I put a ground plane on the bottom. I put a power plane on the top. It did successfully route this board. So this would probably actually be a usable 2-layer board. But it has some negative properties. So looking around the ground plane, let's find a ground, maybe down here. You can see what our ground plane ended up looking like. So the ground came in here at this 5-volt connector, kind of got a little bit of grounding, and then we had to kind of jump down to another polygon. We had to kind of hop over a polygon and get down here. It's just all disconnected and got small traces. So I probably could have done better had I manually laid out some of the ground traces. So for example, I could have at least run a trace around the outside so we didn't end up with all these disconnected sections. But still, this is quite a complex board, and I'm not sure how much better I could have got at the ground plane than this. So let's take a look at the power plane. It should be up here. Yeah, so here's my 5-volt. So it comes off of the 7805 regulator, goes over to a capacitor. It's kind of got some chunks of polygon going down here and then some traces. Very little polygonization of the 5-volt layer. So you can kind of see the situation we've gotten into. We've got a big board, lots of components, and our power and ground signals that we'd like to be clean and stable. Just because of the complexity of our board, it's hard to do a good job with those polygons and get good coverage. So that brings us to going with a multi-layer board. So a multi-layer board
We could go from the 2-layer board we're at now, we could go up to a 4-layer board. And what are the advantages of that? So one of the obvious advantages is just complexity and density of components. We could put our components closer together, and we can have a lot more traces on a multi-layer board just because we have a total of 4 layers that we can use to route stuff. The other advantage is better power and ground planes. I think that's obvious after looking at what happened in my first 2-layer attempt. So the other advantage for high-speed layout, this is not a high-speed project. This is an old retro project, but if it was high-speed, from what I've read, you can do much better with the multi-layer boards. Also for EMI, you can do better with the multi-layer boards because you can get some shielding by putting big planes on some of your layers. So I decided I wanted to go multi-layer with this. I contacted JLCPCB, said, hey guys, how would you feel about sponsoring a multi-layer PC board video? They gave me the go-ahead. So I am doing this sponsored video, my very first 4-layer board. I am receiving free boards and other incentives, though I will not let that bias my review in any way. But anyway, let's go on and try to transform this 2-layer board into a 4-layer board. So first I'm going to rip it all up. And we've got to get rid of these old polygons I had on here. Rid of all chunks of old polygon. And sometimes it's kind of hard to see them on the latest version of Eagle. Yeah, there's some chunks of polygon down there. There, I think we've got rid of all the... Oh, there's another chunk of old polygon. Okay, so I've cleaned everything up. So the first thing we're going to have to do is to set up our design rules. So tools, DRC, layers. Right now this is set up for a 2-layer board. Top layer, a big core, and a bottom layer. Via's going all the way through. We need to set up for 4 layers. So what we need to do is we need to go over to our board house, in this case JLCPCB, and see what it says to do. So the JLCPCB has a 4-layer stack up, and we need to set up Eagle to do that 4-layer stack up. And JLCPCB stack up is going to be, solder mask on each side, so a top solder mask, bottom solder mask. Then you've got top and bottom layers. Then you've got something called a prepreg. And then inside of the prepregs, you have the inner 2 layers. Then you have the core in the middle. So we've got to transform this dialog in Eagle over to look like that web page. So what we have to do is to edit this setup equation. It'll tell us what to do here. A star B combines 2 layers with a core. A plus B does the same with a prepreg. So what we need is a equation where we're going to do layers 1 and 2 combined with a prepreg. And then we've got core. Then we've got layers 15 and 16. Now we need to correct these thicknesses. So I'll go ahead and do that. So top layer 0.035, and then isolation between top and the first, the prepreg is 0.18, and then the inner layer is 0.17, and then the core is 1.12, the next inner is 0.17, then over here we've got 0.18 again. So just to sanity check this again, we've got 035 followed by 0.18. We've got 017 followed by 1.12. Then we've got another 017 followed by a 0.18, and then another 035. So a few interesting things to notice about this is the outer layers are thicker copper than the inner layers. We've got 35 or 0.035 millimeters on the outer layer versus only 0.017 on the inner layers. And also the insulation is much different. So we don't have a whole lot of insulation between the 2 top layers, only 0.18 millimeters. Got this huge amount of insulation due to that core in the middle. and then a relatively small amount of insulation down here. So if you're doing something special like a high voltage or high amperage board, you might want to pay attention to these insulation thicknesses and layer thicknesses. That's not something I'm doing here, so I'm not going to worry about them. I'm going to put my two signal layers on the outside, and I'm going to put my two power layers on the inside. So let's just apply this, get rid of the DRC dialog. So now we've got to view our additional layers. So let's turn those on. So over here in the dialog, we now got a route 2 and a route 15. So what I'm going to do is I'm going to put some polygons on those. So on the layer 2, let's draw a polygon. I find these really hard to see on this new version of Eagle. These don't have to be perfect. You just have to kind of close it up. You can make the polygon bigger than the board. You could go either way on this. You could put your VCC layer first and then your ground layer, or you could put your ground layer and then your VCC layer. I've read around, people say sometimes maybe it makes most sense to put the ground layer closest to the signal layer with the most traces. In my case, I'm not going to worry about it. I'm going to put the 5-volt higher, and then I'll put the ground on the lower one. So we'll rename this polygon plus 5V. View, zoom to fit. Then we're going to make another polygon. We'll put them down here at route 15. Again, just draw them bigger than the board. Sure he closes up. And then we'll change his name to ground. Okay, so let's tools. Auto router, are we ready to route? Let's go see what happens. So first we've got to turn these two layers on in the auto router. Let's not continue an old route, so we'll turn route 2 to auto and route 15 to auto. Let's continue. Now for whatever reason, I don't know why, but my Eagle top router always causes Eagle to hang on my computer. I don't know, something about my computer, something about Eagle. Maybe somebody knows, but for me, delete top router will make my life easier. So that just leaves these other 9 route jobs. Haven't changed any settings on them. Let's just tell it to do it and see what happens. So here it's chugging along. Now you can see it's going to get to 100% on like all of these. So before on my 2-layer board, you only get to 100% on, maybe half to a third of them just because the board complexity was so much. But those 2 extra layers going to make this much easier. Our via count is pretty low. On the 2-layer board, I was getting at best with the auto router around 600 vias. Here we're easily able to get around 300 vias. Let's just let it keep going until at least one of these hits finish. Let's keep going until at least one of these reaches optimized level 4. Okay, so that one's completed level 4. This one's got a lower via count. Let me grab it and end job. Okay, 100% finished. It's good to go down here and make sure it does say 100%. A lot of times with Eagle, bad things could happen with broken polygons. Say the polygon connectivity is collapsed or something like that. That would happen a lot on 2-layer boards. Doesn't seem to happen on 4-layer boards. But let's see what happens. So let's take a look at our layers independently. So I want to let's just look at the top layer. Okay, see we've got all these nice red traces for the top layer. Looking much like a top layer would. Bottom layer, lots of signal traces again. Inner layer. Okay, so we can see it's put some signal traces inside on our inner layer. I don't really like this. I don't like it at all because for a prototype board, I might want to cut some traces, of the signals, reroute some of the signals, and these signals are buried down inside of this board. Um, yeah, you can see how it's just kind of chopped up the polygon. And the other thing is, it's just chopped up the polygon. I really want nice whole layer ground and power polygons. It's kind of why I went to this whole exercise. So let's take a look at the Route 15. Route 15 is it's the same thing. It's put some signal traces in here. It's chopped up the polygon. Um, that's not what we wanted. Turn them all back on, and then we will rip up the whole thing. So there's probably more than one way to solve this, but the way that I found to solve it is by adjusting weights in the auto router. So let's go back in auto route, continue, open this up. As before, I'm going to get rid of top router because it causes my machine to lock up. So here, routing variant 2, we're going to change these weights so that they're very high on layers 2 and 15. It's kind of arduous to go through and do all this. There, so that's all of them. Now we can go back here. We could hit save as, and we could save this profile. It only saves the profile for variant 2. But then once it was saved, we'd be able to load it next time into variant 2 without having to do all that typing. I've already saved them for the other variants. So let's load from my saved variant file. So I'll load variant 3, load variant 4, load variant 5, variant 6, 7, 8, 9, and 10. So that was still a lot of work, but it was less work than typing all these 99s in. You can see all of the 99s have been loaded into Route 2 and 15. Now if we start this, hopefully the right thing that we wanted to happen will happen. So we're still having a great deal of success here, but you'll see our via counts are just not quite as low as when we did the routing before. That's because we don't have those inner layers available for signals anymore. They're just being used for ground and power. We'll let it churn away a while until we pick one of these that we like. Okay, let's pick this one here. In job. Look down here, it still says 100%. And now let's look at our inner layers. So let's start with route 2. Okay, this is better. No traces inside the inner layer, and the whole polygon is unbroken. So you might ask yourself, is it actually connected to my components? And we can just take a close look here, and we can see right there, yeah, that is where the first inner polygon, the 5-volt polygon, is connected to a bypass capacitor. Here it is connected to the VCC of this logic chip. It's got isolation between any vias that are getting punched through, and isolation around any signals that are getting punched through. So this looks like exactly what we want. Then if we look at our ground polygon, that was down here on Route 15, same thing. Where was that first one? I think that first one we were at was over here. So ground is punched through to various places on the logic chip, and it's punched through into the bypass capacitor. Looks good to me. This is what I wanted to happen. Then if we look at top layer, should see, top layer not hooked up to grounds or 5 volts at all, because that's all handled by the inner layer. Perfect. Okay, so let's go here to CAM processor. I did not like Eagle's new CAM processor dialog at all. What I want to do is I want to open up the old CAM jobs because I know how those ones work. So Gerber 274X-4 layer. Maybe you could have done this with the new CAM job, but I'm familiar with how the old CAM job works, so I'm going to do that. So it's going to generate a bunch of files. Component side will give us a CMP file. Inner layer will be LY2. The next inner layer is L15. Solder side and SOL. We've got silk screens, PLC and PLS. Stop masks, STC and STS. Cream frames. I don't think we use those for anything, but sure, you can go ahead and make them. Process job. So it's going to do its thing. It's thinking. There, it's completed. And then let's open CAM file, Exelon, generate drill data. Drill data, drills and holes. It's going to go in a DRD file. Process job. And open folder. So I usually make a work directory to put these files in. So I've got a directory here, nice empty directory. Let's sort these by date. And we should have a whole bunch of files. We've got a few more files than we had for the 2-layer board videos that I've done before. There's the LY2 and the LY15. It generated those cream files, the CRC and CRS. I don't think we actually need those, but we'll just move it all over here and give the whole set of stuff to JLCPCB. So how many files? This is 13 files. Looks right. 7. Create a zip file, jlcpcb.zip. Z80 single board computer. And now let's upload this design to JLCPCB and get it produced. Instant quote. So here is our zip archive. Let's open that. It's going to chug away and think about this for a while. So there, it's detected a 4-layer board. Cost for this board is going to be $90. So this is, this is pricier than most of the boards I've done in previous videos, but it's a really big board and it's a 4-layer board. So I think this is a really good deal. This is going to be for 10 of them. So 4 layers, the dimensions are right. PCB quantity 10, we're going to stick with 1.6 millimeter thickness. I think I will make them blue. That's going to add an $8 color charge. We can live with that. We'll keep the cost to under $100. It's about $10 a board. I'm going to leave it on Hazel finish. I think if I went Enig, yeah, Enig would add like another 30 some odd dollars. So I'm not going to do that. I'll stick with hot air solder leveling. Before we actually save this, let's like look at the Gerber Viewer and see what the Gerber Viewer can tell us about this. I always like looking at things in the Gerber Viewer just to sanity check, make sure everything looks right. So the board size looks good. You can see these kind of yellowish areas are the stop mask. That looks good. See all the vias are tinted the way I like them. The top layer looks good. The silk screen is the way I want it. Bottom layer also looks good to me. There is nothing on this Gerber Viewer to view the two inner layers on the 4-layer board, as so far as I can tell. If we really wanted to be pedantic, we could load up a standalone Gerber Viewer and view the files directly on our computer and look at those inner layers, make sure they were right. I actually did do that for this order when I submitted it, but I'm not going to go through that step here. We'll take a look at the analysis, see what the analysis had to say. So yeah, there were some files aren't necessary. So those were those two cream layer files. There's some kind of drill information, some other kind of Gerber information. Those things, it always skips those. But yeah, bottom silk screen with a board outline, that's good. LY2 and L15 generic Gerber file. Those are our two inner layers. We've got our top silk screen, got our bottom layer, our top layer, top solder mask, bottom solder mask, and drill. So it detected everything that we thought should be in there. So this is the part of the ordering process where you'd typically come over here, you'd click Save to Cart, save to your cart, then check out, any of your credit card or PayPal or however you're going to pay for the thing. I usually don't show that part of the ordering process. I did go ahead and submit this order. I think the shipping quote it gave me was around $30. So that gives you an idea of what it costs to get something from China. It's with DHL shipping, usually gets to me in like couple 3 days after they ship it.
Okay, got my latest batch of PC boards. Let's open up and take a look. So here are, these are the boards for the single board computer project. Let's take a look at these. This is the maximum zoom I can do without resorting to the microscope. We'll switch to the microscope in a moment. Board looks good. I can see through the top layer. I can see the top layer traces. I can see the bottom layer traces through the silk screen. Looks as I expect it. Of course, we cannot see any of the inner traces because they're inner traces. They're not visible, but we could do a quick sanity check with continuity checker. So I've got that here. We know we use the inner traces for the power and ground. So if we check these two bypass capacitors, yes, there is continuity down to that one as well. So it looks like the 5-volt trace is doing what we expect. Let's check the ground trace. The ground trace should have gone where we expect. And then we should verify that, 5-volt and ground are not shorted together. And good enough. The inner traces did exactly what I laid them out to do. This is my first 4-layer board. So I'm glad that I presumably have got it right. Silk screen looks lined up properly. The visual inspection is good. Even the very fine silk screen I can read on the traces there. Top side looks good. Bottom side looks good. This is a hot air solder leveled board, so it's got the silver color, not the gold Enig color. That's as expected. Just visual check, everything looks kind of what I expected it to look like. So we'll take and we'll put it over under the microscope. We'll take a closer look at the board under the microscope. Okay, I've got the board under the microscope. Let's kind of pan around and look at it. So up here is the header where the RC 2014 bus connector will go. You can see the silk screen is good and readable. Just panning around, the traces look good, look like what I expected. Silk screen readable throughout. Stop mask alignment looks pretty good to me. Everything looks like as I expected. Kind of a big board is hard to find enough room on my to get a good look at it all here on my workbench. Flip over, look at the back side. Bottom side traces look fine to me. All the vias are tented as I expected them to be. Everything here looks good. Let's try flipping it over and we'll go for maximum magnification. Okay, here we are with maximum magnification. You can see the alignment on the stop mask. Looks good and usable. Moving over here to look at that RC 2014 bus connector. That looks good to me. Just panning around. Just looking at some random IC footprints. Looking at some vias. Everything looks great. Flip it over. Look at the bottom side. Again, starting with the RC 2014 bus connector. Solder mask alignment looks great. Traces look great. Pads look good. Just kind of moving around. Everything looks good and looks as expected. Okay, so I finished soldering most of the components. The only parts that I've skipped for now are these Cherry MX key switches. I'm skipping those because I want to test the rest of the board, make sure the board design is good before I solder those on, because those things are fairly expensive components. The rest of this is pretty much all just sockets. You might notice this thing over here where the voltage regulator is supposed to be. That is an Z80SBC switching regulator that substitutes in for 7805. So I tend to put those on the boards because they're more efficient, give off less heat. Slightly modern modification. You could put a 7805 if you wanted to, though you may have to heat sink it. This doesn't need heat sinking, so I kind of like using the Z80SBC switching substitutes for the 7805. So let's actually put some power to it. Good to check the power supply section. Turn it on, no smoke's coming out of anything. And we should just be able to check just on any footprint and see if there is voltage. And there is, there's 5 volts. Okay, so that proves our 5 volt supply is good. Now I'm going to actually populate the chips on the board. Okay, so I've mounted the rest of the components, all the switches, the LED displays, and the DV9 jack. So let's turn it on.
Hit the reset button. Oh, it's interesting. Something was actually writing to one of the displays during boot up. Let's go to CPM. And I've actually put together a short demo to show this off. Copy, paste it into the basic window, and run it. So what this is doing is it's displaying 2 different 16-bit counters, one on this side, one on this side, and I can use the buttons to control the counter. So the top button will turn a counter off. Then we've got increment by 1, increment by 4, just going faster, increment by 16, and increment by 64. 16, 4, 1, off, and we can do this with the other one. So that's just a quick demo of the display capability and the keypad. I'll probably be producing a much more in-depth video on the overall design of this and on some more demos with it, and using some more of the components like the PIO and the CTC, maybe some design stuff, maybe some talking about the slow stepper and the single stepper and that sort of stuff. So that video will be coming. This video is mostly just a quick build and try out video.
Thank you for watching my video. Please visit my website at www.smbaker.com for more electronics projects and sandrail stuff. Bye.